Okay, everybody. So welcome to the colloquium of Department of Mathematics. Uh, we have Professor Nandakumaran today from Indian Institute of Science, Bangalore. And a special thing about him is that he was my PhD advisor. So it's my honor to invite him here for the talk for our department. And the topic of the talk will be Hilbert Uniqueness Method and exact internal controllability for a problem with imperfect interface. And this is an article which is accepted in it is accepted in applied mathematics and optimization. And this is a joint work with Sara Monsurrò and Carmen Perugia in Italy. These two ladies will also be talking for us in some time, maybe in a couple of months. So, Professor Nandakumar, it's floor is yours, and you will be having something like 50-55 minutes, and last 5-10 minutes we will keep it for the questions and comments. Okay.
Yeah, he was also my postdoctoral advisor and friend in India. So
thank you very much. Thank you for the invitation. And yeah, I think I have two of my students here. One is Ranjit, who is currently a PhD student, also Bidan, who is a faculty in IIT Ropar. And I think Abu could not join, the other student could not join. And maybe Ayappan also forgot about it. Anyway, it's nice that I'm talking to my familiar people. Thank you, Rajesh, also for joining and other participants. So I will share my screen. Can you see the screen now? Devi?
Yeah, I can see the screen. Yes.
So I will make the full screen more. Okay.
Mm-hmm.
Thank you once again. So I want to talk about what is Hilbert Uniqueness Method and exact internal controllability for an imperfect interface problem. Since it's a colloquium talk, I will be giving, I will spend only half the time, second half only about my specific work, but to address the general gathering, those who are not working in exact controllability, I will give a brief introduction about what is this exact controllability and what is this Hilbert uniqueness method. So once I do this in the first half an hour, and then it's enough to specifically explain what we need to do it in the specific paper which we have studied. As already Ravi said, this is a joint work with Sara Monsurrò and Carmen Perugia from Italy. And I thank them for the joint work. It will be coming in applied mathematics and optimization. So I will do a brief introduction, linear controllable system and linear wave equation with controls on the boundary. And that's maybe 10 minutes or 15 minutes. And then another 15 minutes, I will do the Hilbert uniqueness method. And the last 25 minutes or so, I will do internal controllability and what is this problem and what estimates basically you have to look for. So let me start with the beginning of a control system. A controllable system generally consists of a set of equations. It can come in the form of ODE, PDE, or discrete systems, and gives a trajectory. So if it's a finite dimension system, it will give a trajectory xt in Rn. If it is in PDE, it may belongs to a Hilbert space of infinite dimension. The state equations, the static or the dynamics, will also have control U, which you can influence the state. So you can change the state, like sending a trajectory to the or sending a missile, but applying the suitable control, you can change the path. And the aim is to reach a desired state. If you have an enemy place, you want to hit the enemy plane, you will hit, or if you want to put a satellite, and you can change it. You have to apply control, not necessarily continuously, but we study continuous control, but there are other controls more physically relevant also. And we have to achieve all this with the minimum cost if possible. Minimum cost compared to some cost function. Cost function can vary accordingly what you want to decide, what you want to minimize it. So for example, you will have a ODE system like this, and UT is the control, YT is the state. And if it's a PD, then just making an example, not necessarily the wave equation. It can be heat. There are problems if you consider heat equation. So that there are many other controllability, exact controllability, approximate controllability. These are all depends on the features of this wave equation, hyperbolic equation. All the properties of hyperbolic or wave equations the properties can change the concept of thing. This is I given it as a distributor control because it's in omega cross RT, but you can also apply this control along the boundary. We will quickly see that. And then for example, if you have a linear system and this is YT is the state and UT is the control. So the control problem can describe given Y1 in Rn, does there exist a control U so that it will reach the desired place you want it. So Y1 is given approach. So given in Y1, can you find U? In case, because once you fix it, U, YT is uniquely fixed. And then it may not go through Y1. So you want to see whether that trajectory will go through Y1. Does there exist? In general, that's not true. Even for, if we say the system is controllable, if the time is T is independent of, or for all Y0 to Y1, a common T happens, then the system is uniformly controllable. You can know, so not that all systems are controllable. There are very trivial examples. I will not get into that now. And then there is a famous thing in the 1960s, this is studied, and there is a known as Carmen condition, which is a rank condition corresponding to a controllability matrix. I'm not explaining what's a controllability matrix here, but then the controllability is equivalent to the a rank condition, which is a necessary and sufficient condition for exact controllability. And you can also consider non-autonomous systems, and conditions can be given in terms of fundamental metrics or controllability Gramian metrics. All that is associated, studied for the last 50, 60 years. The condition is in terms of the dimension n, which is infinite in the case of PDE. In other words, the state is in an infinite. So there the trajectories are moving in an infinite dimensional space, and this method it don't work, but still we want to understand something. So many times there is after controllability, there is an associated notion, what is called an observable system. Many times it may not be possible to obtain the state exactly, or it may not be necessary. Probably possible to observe certain quantities related to the system. This is what is called a partial information. Y is your full state, so you may not be able to get Y completely, but then H is a matrix. It's a linear observation. You observe something. You may not, suppose you have n components in a trajectory, you may be observing only one component. Okay, you may not, that's why it's called a partial information, or something you may observe. Okay, and then how the control U should be employed based on the knowledge of W, so that the response Y to behave in a desired manner. So this is a very general terminology of a observable system. You observe your observable quantity, which is a partial information. Whether this partial, if you have a partial information for sufficiently large time, can you recover your state? That's what is called. So controllable is an uncontrolled system. So the observability thing, you have an uncontrolled system and you have an observation. And the question is that if you can observe T for sufficiently large time, can you get back my state? That's the whole thing. So a partial observation, partially, so you can think that if you observe a student just for one examination, you may not be able to tell, but if you observe a student for sufficiently large time with many examination, then you can say something predictable about the student. That's a kind of an analogy if you want it. So, so observing something partially for sufficiently large time, can you look back that one? Thus, measuring some quantities for sufficiently large time, can one recover Z? That's what observability. Again, there is an equivalent condition in terms of the dimension of the observability matrix instead of controllability metric, not suitable for PDE. But then observability can be achieved if we have an estimate like that. Suppose you can prove this estimate that you are ZT in terms of your observation. It may not be possible. You have to see that because it's a partial observation, but partial observation is something. So this is one sufficient condition for observability, because if W equal to 0 for all top, then Z equal to 0. And estimates are part of PDE analysis. That's why I stated one thing. So, so why this is PDE, and that's why. So what is the relation between observability and controllability? So there is an equivalent criteria. A system one is controllable if and only if adjoint system together with this observation is observable. That's an interesting if and only if condition. So you're observing an adjoint system, but adjoint system is an uncontrolled system. You have to understand there is no control there, but you make an observation like that. This is your observation. So controllability is equivalent to observability for this thing. The other one is y dot equal to ay plus bu. That's the thing. Okay, so the philosophy is what I want to carry to PDE. And uncontrolled, so the controllability is can be achieved if you have an uncontrolled system, an observation, and an estimate, an ideal procedure for PDE. And this is what I want to describe through HUM method. That's a quarter of my talk. So let me go to the next quarter.
Nandakumar, just a minute.
Yeah.
Can you just briefly recall what you mean by observability? Meaning, if
yeah, this is observability, linear observation. That if WT equal to 0 for all 0 to T, then Z equal to 0. Identically 0.
And quantitatively, it means the norm of W controls the norm of...
Exactly. That's why for a sufficiently large time. That's a one sufficient condition. It's not a necessary condition.
Okay,
yeah.
Thank you.
This is only a sufficient condition.
Yeah.
Just to show that you want to write controllability, observability in terms of the estimate. But then you have an if and only if condition for observability. Okay, in terms of the dimension.
Yeah, thank you.
Yeah. So now let me go to Hilbert's uniqueness method. I cannot just fully motivate you the Hilbert uniqueness method, but there is a very beautiful motivation using the penalization method, but that needs another half an hour or 1 hour. So I will not get into that, but I follow the procedure just described now. So again, I'm taking a very easiest system. You have a linear wave equation. And then you have, so the control I am applying boundary, but you can also control apply internally. YTT minus Laplacian y is equal to U. You have various ways of applying control. You can consider various other problems by Laplacian and all that. And the method what I am describing here is not restricted to just this wave equation. You can have many systems. Laplacian can be replaced by general metrics, etc. But the idea is to describe what is this method. So the control I apply, and then sigma naught is one part of it. So gamma naught, so this is the gamma naught, one part of the boundary, and gamma 1 is another part, and sigma naught is typically gamma naught cross 0 to T. So over this time, okay. This is the with respect to the parabolic boundary. So you get the part of the parabolic boundary. So so you can apply fully also. You can apply internally distributed control, but in PDE generally the boundary controls are more, because boundary is the one you have the accessibility, not inside. Inside is always not accessible. Or at least suppose you want to control something in a big region like a river or something, you can work something on the bank of the river or in a neighborhood of the boundary. So that's more accessible. Okay, so again here, so you have two data, y0 to y1. Keep this now, y0 to y1. First time may be a little difficult to get back, understand this method, but it's one of a very nice method. So given initial data, and a given finite data in some controllable space. So you have plenty of controllable spaces depending on how you choose the control. Does there exist a control V in some control space and a time t, so that the unique solution y satisfy yt equal to z0, yt at t equal to z1. So something like you can, whether you are a membrane is vibrating, you are applying control so that you want to stop the vibration or you want to have your desired vibration. That in that case, stop the vibration means you want to stop both. So that's why yt equal to 0 and yt at t equal to 0. If t and v exist as above, we say the system is controllable in time t, and indeed it is independent of the data, it's uniformly controllable. If it is controllable for any initial data y0, y1 and 0 final data, then the system is said to be null controllability. And for a linear system, what I described there, the null controllability is equivalent to controllability general in the system. So for a linear system, if you can move from one point to another point, from at that point you can reach to a different point. So it's enough to control to the 0 thing, but linear system you can get the equivalent to the controllability. But that's not true if you want to study nonlinear system or fluid flow systems and Navier-Stokes situations. People generally study only the null controllability. So the question, there are plenty of questions, whether a given system is controllable. If so, find the control and controllable space, control and controllable time. So you want to identify the spaces, time and control. Whether to apply control on the entire boundary, is it enough to apply on a part of the boundary? These are the questions, because control is an expense, cost. You cannot apply, and it may not be accessible also the boundary. And find the optimal control according to some criteria like energy minimization. So that's a kind of optimization. Actually, the HUM method can be motivated just by looking at the last point. You look for the, assuming that there is a control, you look for the best control with an energy, and actually these equations, the method will come automatically. So just I want to, as a side view, I want to mention one of the very interesting paper, tough paper, and it's based on geometric optics and micro-local analysis by Bordo, Lebo, and yeah, this is not Lebo, last letter is U, and Rausch in the 90s, so very almost 30 years back. So you have a control region, and that paper essentially tells you that if you start a geometric ray, anyway, if the ray is moving and then reflecting, and at some point it should reach the control region. So if you have a control region, more than half of it here, then the system will be controllable. But even if you leave out some region like this dotted line, there are rays which will get trapped, and this ray will never reach touch the control region, and you won't achieve the controllability. So this is a kind of a wave propagation. You have to propagate the information from the control region to other region. So if there are rays like this, it will not get. So even if you leave out a small region and like this, you won't get controllability. On the other hand, if you take more than a semicircle, little more than an epsilon more than semicircle, you will get the control region. So for example, if you have, that's why in the, if you want to study homogenization or perforated domain, you have to study, even if you have two holes, and then if this is a domain, and if you don't apply any control here, and if you apply full control on the boundary, you won't achieve the controllability. And so you have to have some, because there is a trapped ray here, which will never think. So that's a very nice paper which I'm giving today. So there are semi-group approach to certain operators, and then you also, so what I'm going to describe now is the Hilbert Uniqueness Method due to Lyons. Is maybe in 1970s or 80s they introduced. Why I describe here, this is more of an operator theory approach, and the earlier one I said it's a more of a micro-local analysis and other things, more geometry. And this is more of a PDE techniques and home grains type uniqueness theorem. End of it, the principle may be the same, but then the way we like it, the PDE people may enjoy the Hilbert Uniqueness Method because it's exactly as you see an observable system. You are studying for a PDE and an estimate. No control problem is coming into picture. That's the whole idea. So, let me follow the procedure from ODE. So you consider an uncontrolled system. So you see earlier there was a control on phi equal to 0, but there is a control here. There is no control. So you removed the control and you consider an uncontrolled system, and then you consider an adjoint system. In the present thing, you may think that it is a bit artificial. What I'm saying that it's not artificial. There's a separate way of explaining and motivate this using my penalization method and optimal control. When you want to look for a bus control, all this comes. And this is the control here. So, but then this is an adjoint system. And of course, since it is a linear wave equation, whether you put conditions at t or other things, it doesn't matter, but you have to view it as an adjoint system. And since it is reversible, we have no problem, but you have to put conditions here. You see, so my final condition, so I am looking for null controllability because linear systems, I said, I already told you it's enough to study the null controllability. So what I want to achieve, I already put it through my system. Now it's only the question of my choosing V. So psi also satisfy my, let me go to my equation once more. See equation. So I have taken this psi without initial condition, but I put final conditions which I required on null controllability, and then I am putting V. So what I want here, so if I go back to this equation, if I can choose V in such a way that my psi also satisfy my initial condition, then I am happy because I want, I will get my controllability. And if you taking clue from the ODE, I want to choose this control as an observation coming from my uncontrolled system. Okay, what is the observation I have to make, which is turned out to be my control, and I will do it. So analogous to the case of ODE, and it's an 5 and 6 can be referred as an observed system. Here the boundary control V is the observed quantity which has to arrive from the solution phi of y. Okay, so if you can choose V, so let me recall this equation. If I can choose V in terms of phi, in terms of phi suitably, because I have choices. I have choices of my initial condition. I have not fixed what are all these initial conditions. So by phi naught, phi 1 varying, I will get a various choices of phi. And for the various choices of phi, I choose my observation. I will get various choices of my observation. And if one of the observation leads in such a way that psi satisfy my initial condition, then my controllability is achieved. So this solves the null controllability problem, since we can take then y equal to psi. Okay. So the question is, now question reduces to a 2 PDE problems. Is it possible to vary phi naught phi 1 in a suitable space, which implies we vary in some other space so that psi 0 psi t 0 covers the entire controllable space? So it doesn't matter, so that you will have the controllability. So by varying by phi naught phi 1, this way covers the controllable space, and that means you have the controllability. Okay. In other words, observing a certain quantity related to phi for sufficiently large one, can we recover all the initial states? That's the putting it in words. So partial information for large time, propagate the information to all states. In simple language, I can put it that way. So what is the quantity to observe? What is the corresponding estimate? Of course, I made a natural choice, but for the first timers, this natural choice may be little difficult. I told you, you have to do a little bit of analysis to feel that the flux across the normal derivative outside, that's the quantity you, so that's why it's a natural choice. One immediate natural choice is either phi or your how much flow is there, how much normal derivative is there at the boundary. So one quantity which can possibly work for you is the normal derivative of it. Not necessarily always, depending on the problem, there are other choices. So I will just make this choice. So I rewrite now my problem, a joint problem with the control V. I expect this control. This is the form of the control. I'm not saying that this is the control because I don't know for which phi this will turn out to be my exact control. But a possible choice of the control which may work. So given psi, I choose this control. So it's become a control means it's not a control that way because phi is coming from a known problem. Okay, but I'm giving you a choice. End of it, it will turn out to be the control. And so I can set up indeed to understand the well-posedness. So there is an issue of well-posedness because d phi by d nu is not a very strong space because phi is a solution to your PGE problem, and d phi by d nu at the most it can be L2 function, and you are defining psi its boundary as an L2 function. So psi cannot be defined as a weak formulation. These are all issues which may come up, which I may not describe it here in this talk. But then this I want to warn you. And even d phi by d nu estimate, L2 estimate, is not the standard estimate you get from the existence and uniqueness. Okay, this is what is called a hidden regularity. But even that hidden regularity is at the most in L2 function. But you typically need something like h half to have a variational formulation. So you have to understand this solution not in the normal weak formulation form. You have to understand what are called transposition method, of course, which I will not describe it here now, because that's a more weaker notion of it. Okay?
Nandakumaran,
Yeah.
one question. So why do you say it's natural, the choice?
That's what I say right now. It's bit difficult with, but little bit of an analysis, like what you say, if you look for a minimizing control, okay, and you do a bit of a minimization method, and there is a what is called a minimization via penalization. When you do the bit of an analysis there, mathematically this quantity comes out to be naturally there. Okay.
Thank you.
Another thing, possibly, if you are, that's what is needed. We have to do a bit of an analysis. Another possible thing, this is the quantity you see a motion, right? The derivative. That's what you observe at the boundary, phi or d phi by d nu. That's what one way you can observe for a wave equation. Nothing else. That's first two quantities typically you observe at the boundary. Phi. Okay. Yeah, more intuition needs more analysis. There may be other things. Yeah, so this motivates us to a defining. So you want to understand the correspondence between phi naught, phi 1, and you want to understand what initial condition. You want to recover this initial condition. Okay, so phi naught, phi 1. So you set up a mapping. You get a psi t 0 and my psi 0. And I told you phi naught, phi 1 is a smooth data. And hence phi is defined smoothly, no, in the normal weak formulation. But psi is a transposition method defined in a very one level less. So here phi naught is in H1 naught, but you get psi 0 only in L2. So the solution in transposition method is looked in H minus 1 L2 or L2 cross H minus 1. So it's the transposition solution gives you in the L2 and H minus 1 space, not a H1 and L2 space. Okay, transposition. Whatever it is, so you associate this mapping. So once you do this one and do the normal mathematical trick, do the integration by parts. That's only tool we are having. PDs, people are always survive with integration by parts. But how you integrate by parts, what kind of multipliers are used, these are all important issues. So multiplying the equation for phi by psi and psi by phi and do an analysis. And then you want to, so this is an operator here. So lambda operator. So you want to understand typically lambda x. Okay, so your idea is exactly to prove the ontoness of lambda. But once you prove the ontoness of lambda, you say that for any initial condition, there is a phi naught phi 1, and you can get the control d phi by dt. Okay, so once you know the ontoness is there, and this is going to be your control space, namely the L2 cross H minus 1. So every H cross H minus 1, you can invert lambda if you prove it an isomorphism, and then you get an initial condition. Corresponding to that initial condition, you get phi, d phi by du, and you get your solution. So this is nothing but this. You can do a computation, and you can show that this is nothing but this. That means you have d phi by d nu. So you can think that d phi by d nu is your partial information. And you basically want to show, so the whole controllability problem in this case reduces to that of proving the norm defines an equivalent norm in this space. Once you show that, because this is how you find it's an isomorphism, right? If you have a t, if an operator t, you want to prove it, you have to compute tx, and that's a norm equivalent to this norm, and then it will become a thing. So you want to show that this partial information is no. Of course, estimating this in terms of the norm is a direct estimate. That's a hidden regularity, but reverse estimate is called an observability estimate. So if you prove that, you will get the exact controllability. So this is the, yes.
One more question.
Yeah.
Sure. So this observability estimate is then in some sense equivalent. So it's you're interested also, I mean, in some sense, the subjectivity of lambda, or
you want a isomorphism of lambda, basically. Okay. Subjectivity of the lambda. Yes, more than that. You get both inequalities.
Okay.
You have both sides. So you have an isomorphism. And this is the hidden regularity. This is, you can call it a regularity of your wave equation. The second inequality. The first inequality is and first inequality is not always true. That's the whole issue. Because you are applying control only on a part of it. Even we do not know that is true or not. But so you need to have so this way inequality is always true. Second inequality, even though it's hidden, it is true. Not for any sigma. Okay, for full sigma, it is always true. For arbitrary sigma, nothing is true. Only a portion of it. You need there are some control regions which I explained. And this is an energy corresponding to that. And the energy is conserved, and you have your E0. So you want to basically prove this. And the second part is a regularity. First part is your observability estimate. Exactly an inequality. Now you see, you have this is called an observability estimate. In general, this is not true, and it depends on the control region of the boundary and largeness of the time, because you have a finite speed of propagation for your wave equation. So you cannot transport a data or an information one place to another place, and it takes time to transport. That's why you need a sufficiently, and in general, it depends on the diameter of the region, etc. So this is already I told you. The beauty is that controllability problem reduces to that of estimating terms related to solution of an uncontrolled problem. That's the message. You are only estimating a term. So you see, if you look at this one, this is an estimate of your PD, uncontrolled problem. Nothing else. Nothing else is coming. You are just one equation, which is a normal wave equation, and you are estimating for that wave equation. That's it. Okay, that's why this is so beautiful. The method, the reason is method is algorithmic and hence constructive. Numerical schemes are available, and this precisely shows that if I define a new norm in this space and is equivalent to the usual norm, so this defines a new norm. This derives an uniqueness result. You see now, if you have a observability estimate, d phi by d nu equal to 0 sigma naught implies phi naught phi 1 equal to 0. That implies phi identically 0 by the uniqueness of the wave equation. So this data is the full data for you, full information, even though it's a partial information. If that exists for some big time, and a proper boundary, and then you will get the uniqueness result. In finite dimensions, there are much more deeper result, but then in infinite dimension, the observability estimate is stronger than your uniqueness theorem. Okay. So in the maybe last slide for this. So you start with find y0, y1 in this space. That's your start. Solve this equation to get phi0, phi1 in this space. Solve for phi using and compute d phi by d nu, and then solve for psi with this d phi by d nu, and you are controller. Then the control is d phi by d nu, and the solution y equal to psi satisfies this equation. Thus, it is enough to establish the estimated, which is of course technical, what is called a multiplier technical. So it's not true for arbitrary sigma naught. But then just one, there are some control regions I can define. These are all again intuitive pictures are there. You start with any x0 and define this one. I can define a region what is called x in gamma such that mx naught mu x is greater than or equal to 0. Gamma 1 is gamma minus gamma naught. Okay, and so this is an intuitively picture, except x0 can be viewed as an observer. So suppose you have a circle, your omega, and x0 is at the center. So then your gamma naught is full domain. So it's exactly the region which is concave to the observer. That means it's part of those regions which you cannot see basically. On the other hand, if you have a thing and your x0 is outside the domain, then you draw the tangent, and this is convex to you and this is concave to you, and your gamma naught is exactly this region which this observer do not have an access. And that's the place you have to apply control. When you can watch somebody, he may not do any mistakes. If you do not watch, you need somebody else to watch. That's what basically tell. You need to apply control in that region. There are advantages. So when you do an x0, so there are advantages. If you x0, you have to apply control everywhere. Then you can reach controllability at a faster time. So the controllability depends on the x0. See from x0 to the domain. So if x0 is interior, your time of controllability is just the diameter, but x0 is outside, the controllability time is much thing. So you have an advantage and disadvantage. So if your observer is outside, you will achieve controllability by applying controlling. But you see, even if x0 go to infinity, the maximum you can reach is the semicircle, and in tune with our Pardo-Lebo result. You need to apply more than half the region. Even if x0 go to infinity, it will never touch the center, the semicircle. And there is a controllability. So let me note that already I explained all this. HUM is very general and can apply to many other systems. And the interesting thing, this is what important for. There are many controls driving the system. Once you have one control, you can actually produce many control, but the control given by HUM minimizes this among all control driving the system to rest. That's what is the minimizes the energy of this system. Yeah, now what I'm going to present quickly, maybe another 15 minutes. The joint work. I will go through quickly because the ideas are clear, and anyway I'm not going to do a technical thing. So you have two regions, omega 1 and omega 2. Omega 2 contained in omega, and there is an index. So it's an imperfection problem with two PDEs, one here and one here. Omega 2 is inside, and gamma is the internal boundary, and d omega is the external boundary. So this problem is not the controllability problem, but normally this is studied by so many others, including these co-authors. There are several papers, not on controllability, but other optimal control and other systems. Okay. Yeah. So let me define. So I will take a small region inside omega 2 here, and also take a small region. These are all my control regions. So there are several questions. It's only an initial paper, but then we are not able to get rid of few things. Typically in this paper, we want to get rid of two more things. These are two open problems. Some of one maybe I'm hopeful, one I don't know. Both I feel that it's technical, but I'm not able to, or we are not able to get rid of that two things which we are actually not fully happy with the paper, but okay, it's still okay because of the analysis. So you have two regions, one omega 1 here. Typically, I would like only control in omega 1, not inside. Yeah, but not able to do that. So, but then I have to apply control fully here, but exactly like that part of it with the conditions I have defined, I can apply on a portion of it. That's possible. But then there are some more geometric conditions which I may not elaborate much here. Some star shapes and things like that. So these are all the things which we are not able to do it. So I'm studying of course you can apply boundary control. Okay, so but I am describing the internal control. We have another paper with both are similar. So one paper here and another paper in a slightly lower journal. So it's okay. So I work with, so I'm applying control only in omega 1 and omega 2. So you have two equations now. One in this region, omega 1 region, another one in omega 2 region, and I am applying control on the omega 1 for the first region and omega 2 in the second region. And these are all standard problems studied by other authors. Not, as I said, not controllability problem, but then you have an interface condition. This is an interface conditions, and this is the outer boundary condition, which we have taken there. And this is your initial data. Okay, because there are two things so basically one condition only, but then since it is omega 1 and omega 2 are two separate regions, we are writing down everything separately. The PD is separate. That's what you have to see. It's not a full PD with interface condition.
Nandakumaran?
Yeah. Yes.
There are two transmission conditions. I understand one, but the second one, what does it say?
This typically say that normal derivative is proportional to the jump with some hx function. That's all I can say. I don't know exact physical relevance, but basically this may be the jump. This is your conormal derivatives, right, across the boundary. The left side is the right side is fine. The left side of the second condition is the conormal derivative of the u1, and that is proportional to the, not exactly proportional. It is the difference in u1, u2 with h. I don't exactly know because I have not got into the physics of it. But this is the condition they use it in the applications. So maybe I will understand that later more of that condition. Is that okay? Not satisfactory answer, I know that. Because
no, I mean, I was a bit confused because I was trying to see whether the two conditions, they don't interfere with each other. That's my...
Yeah. But yeah, you typically need that kind of two conditions, right? It's not.
In other words, Rajesh is worried about the well-posedness of the problem.
Yeah, it is they have studied. These are all they have studied. Not we have studied, but these problems of well-posedness are all studied by that group. I think even Patricia.
Carmen and Sara studied such problems.
All these problems and well-posedness. Of course, you need to be hx greater than or equal to h naught greater than 0. You need such conditions. So the well-posedness is there. It is studied.
Even you can see the paper of Patricia and her group. They have studied a lot.
Yeah, they have studied.
So well-posedness is not gone, right?
Yeah, it's not gone. It's not. Well-posedness. Okay. It's a two independent conditions, but full condition. You need the kind of full condition, boundary condition, right? Basically.
Yeah. Okay.
And thanks. I can explain you the physical thing later, yeah?
Okay. Yeah, maybe at the end of it. So, so don't read about the technicalities. So I'm just stating the theorem, we can achieve the controllability. Okay. I will come to that, the spaces. These are all stated, but I will, there is a control. I will explain to you the space. The solution is in a weak space, exactly like L2 minus H minus 1. This is something like H minus 1. Okay, H gamma prime. And then Yeah, this is not the very strong result. If we would like to have it, we would like to get rid of all these assumptions which I mentioned. And that is why we are not fully happy with the result. We tried for some time before sending it, but then we did not find to overcome that thing. Okay. So you start with U0 U1, and there is a control, and then the control satisfied with some time, that one. So we'll not come back to this theorem, and the more interest is what are the things. So these are the spaces, because you have only on the outer boundary you have the condition, and your H comma. So we are writing V equal to V1 V2. This is in omega 1 part with boundary condition, and V2 doesn't have any condition because it's only the conditions are defined in terms of the normal derivative. So we don't put any condition, and you have your equipped with that norm, and then W is also like that. This is the space we look at it. L2 we cross, so V2 is in this thing with respect to T, and these are all typically standard space. Since we are working with this imperfection problem, you have to separate. So otherwise, it's not very surprising spaces. These are all very. This is the one we have put it. They use it also in the weak formulations and all that. And you can have the corresponding norms. These are all very natural norms, because this is where you are looking at L2, and then you have H1, and there is no summation here. Sorry, this is a wrong symbol. I was trying to connect, write it a simpler expression, but after putting summation, I thought you can't because the spaces are different. Then I forgot to remove the sigma. There's no sigma there. Okay. And the control we will be so the control space is going to be W prime, the weaker space, and there also there's a problem. You can actually look for whether we can get a better control, but again the observability inequality, we are unable to prove a better observability inequality. So there are quite a few things to be settled in the sense that new issues. Okay, and we seek a control here, and this is your controllable space. This is something like L2 cross H minus 1, which I have said. Since the controllable space is weak, which is also the initial data space, we seek solutions in the sense of transposition. And the given system is said to be exactly controllable. This is the definition we have already given. So can you find a control here so that it reaches here? Again, the controllability is equivalent to null controllability. Okay. So what is this HUM and observability? So you have an uncontrolled system. Exactly. The only thing is that system is changed. Otherwise, everything is fine. And then you have a weak formulation. You can give this weak formulation. This is what I say. It's already studied, and you can get your solution because now the data is smooth. In this case, the data is smooth. But then when you come to the adjoint problem, this is going to be the form of your control, and which is in a weak space. Okay, so the form of this is in W prime. Okay, so you have a control in this form, and you have to define everything in the sense of transposition. Okay, and these interpretations can be given. So that there is a sense of transposition via the adjoint method. So you can say that weak transposition method you integrate twice. In the weak formulation, you basically integrate only once. Transposition method you integrate by parts twice to construct the class of test functions. That's all we will do basically. So the control is going to be in this form. And then null controllability problem is solved if this happens. Okay, if you can choose control in such a way that this has to be reached. It's exactly the idea and method are exactly the same. Thus the key point is to choose the initial data so that above initial conditions for theta are satisfied. This again, now I'll quickly go through. I will not spend much time, and I don't have. Can I take a few more minutes, Devi?
Sure. So
you
have
a few more slides. So you exactly define this operator as defined earlier, and then the controllability problem is solved if you can produces the subjectivity. So if we can solve this, and exactly we prove it. So the fact is that we prove that lambda is an isomorphism. So you have to do a bit of analysis. When you do a bit of analysis, you end up with this case. This is the norm we have to prove now. So that's what we get. So you want to, so to prove the lambda is an isomorphism, you have to prove an observability estimate. Essentially, you want to show that this is an equivalent term. So let me, so you have to prove lambda is an isomorphism between these things if the right hand side is an equivalent norm. And one inequality of equivalence is the direct estimate from the homogeneous problem, and the lower estimate is the observability estimate. And then you have this control, all that. So let me quickly do it. And again, then look into your energy system, and then you will see that energy is conserved, and you get that one. So hyperbolic systems, you should look for this conservation of energy. Okay, and then you exactly prove this. So the observability estimate is proved in 2 steps. First, you prove this estimate. It's not Z1, it is grade Z1. From that, you prove this estimate. So what we would actually like, I don't know, that is a very ambitious thing, whether we can even get rid of these things. And please note that this E0 is in full omega 1 and omega 2, capital omega 1 and omega 2. This is only on a small region. So you are controlling that full estimate, full energy with an information only in that boundary, small neighborhood of the boundary. That's the point. But then what we would have liked to get rid of even this Z1 and prime and Z2 prime, then you get a better control. And we could not do that. Okay, so and then if you put that everything, we have an equivalence of the norms here. So this is what best we could do with omega 1 conditions, geometric conditions, and all that. So that's what he said. We may have to work on it, but something intuitively I feel that it should come thing. With just one way is that one thing we want to really do is that I want to get rid of this term in this estimate. But then not able to understand how these equations are transmitting through your interface. So that means I want to understand this omega Z2 prime, which is divided in omega, and the information is transmitted through the interface. And then how do I get this? Only this portion, which is difficult. Not I don't know. We don't have an idea. There's no contradiction also. Okay. Yeah, this is what we get the equivalence of the norms. And you have indeed you have the uniqueness. If you have Zi equal to 0 in this portion, then Zi equal to 0, the full portion. Okay, so you have that uniqueness result. So you see your control is in a slightly, it is a distributed control in a small region. I think I have done it. Yeah. Thank you, Ravi.
Thank you so much, Professor. Yeah, these are the books.
Yeah, these are some
by
Professor. There are also some video courses related to these books. So, the video course for this book is given in 2014, but this 2020 and 21 we are given in 2 sets of video courses, 20 hours each. So you have 40-hour lecture of video courses for both books. Yeah,
perfect. So it's the time for comments and questions, but quickly, please. We have just 3 minutes left.
Yeah.
Nandakumaran, I have one more question. The last year work, again, it was quite surprising for me to note that the control takes a different form in the exposition. The first part was a normal derivative of some function, but here it's like Z double prime.
Yeah, that is true. That is not surprising. Even for the wave equation, you put internal control, it comes as phi only, not even phi prime. Even for the wave equation, so this is an internal control. This is a distributed control. This is not a boundary control. The control here. And this is the same thing when you deal with the normal wave equation. which I have not explained. If I do a distributed control, your control is going to be phi, not d phi by d. Because distribution, that's no meaning, it's not derived.
Okay.
So I can do that. So let me go to that thing. Yeah, when you have, instead of this control, if you apply control on the boundary, and this control will happen to be the phi, basically. Okay. So that's not surprising, because it's, if it is surprising, it's surprising for the Laplace thing. It comes, so you see, you put a control here, and it comes from phi. Instead of, you take y equal to 0 condition and put control here, and the control going to be minus phi or something in this case, minus phi. So you are actually estimating integral phi square in a small region, giving an energy is estimated with a small region. There are various weaker controls and phi double prime, etc. come into picture, because it's a weaker result. So we got that phi in the even in the Laplacian, this particular wave equation, initial estimate is with the phi prime, whatever we have z prime and z. But in the wave equation, they could manage z prime also estimating in terms of z. But in our case, we are not able to do that.
Yeah, thank you.
Yeah,
I
we are
was
not
very
able to get rid of
interested in your talk, and I would be happy to have your slides and also your paper if you can send me.
Yeah. No, paper we are not reached, but you can send the preprint which we are there.
Yeah.
I don't think it is published yet, right, Devi? I don't know. I have not checked.
How am I supposed to know? I don't understand this question.
Those who are interested will know. My interest is over as long as it is accepted, right?
Yeah, but authors should know first.
So maybe
I keep track of your publications, but it does not mean that I can know which is not published, which is preprint.
no, for me, once it is accepted, forget about it.
Yeah.
Then if the interest
But
is
Rajesh, one suggestion: keep track in the research gate. You will get all the information.
No, this
because
I can, Rajesh, I can send it immediately, no issue. I'll send the.
No, I am suggesting him because of other authors also. It's like a Facebook of research. So
I will send you two papers, one about this and one is about the boundary control. Boundary control is basically a little bit of reduction and little bit of work from the.
Okay, thank you.
That is applied research, the mathematics Italian. Interestingly, we wrote that paper and sent it later, but that's accepted first before this.